tonight's game goes well for the Dodgers. And today, as far as our class goes, we'll cover ggplot. I mean, a little bit of it, and so we'll cover some of the basic geometries, the bar and the line and the point geometries that appear in ggplot, and these are probably going to be your most common routine creations that you will create in ggplot2. Those are, I think people are accustomed to seeing bar charts and line graphs and scatter plots and things like that, so that's fine. You know, histograms and box plots also appear, although if you're not in the realm of statistics, box plots, people are often, they don't know how to interpret a box plot, but of course you guys do. And everything, oh, this is the wrong link that's up here. I don't know what's going on there. Link up to the, look at the ggplot2 reference page, and this will have all of the additional geometries. So we're just covering the basic geometries, but here is, you know, layered geoms, and this has all of the different kind of geometries that you have, right? You can create violin plots, which they're actually pretty cool. They're like box plots, except they're histograms turned on the side, except if you're not in the world of statistics, you look at this and you have no idea what this is, right? You have to explain, oh, it's actually a histogram on this side, and there are actually two different histograms being represented. Anyway, but it's worth checking out all of these other ones in your in all the spare time that you guys have during week 5, and you can say, oh, I always wanted to know how to make one of these frequency polygons, and so this is your histogram, but then it doesn't have to be necessarily bars. You can have kind of these a little bit more angular things, and that would be a frequency polygon. Well, anyway, so those are all listed off here, and all of the other things that we can mention also listed off in the reference guide. So the reference pages are actually very good because of the examples that they provide. Okay, let's start off with the bar graph geometries. And most of the time when you create a bar graph, at least, you know, when you learned in 5th grade how to make a bar graph, and then in your intro stats class you had to make bar graphs, it was probably you have your categorical variable over here, and then you create another column with numbers in it, and you say this is how tall the bar is going to be. And if you were going to do something like that, we have to use stat equals identity to tell ggplot that the height that we are using is an actual value that appears in the weight column here. So we're going to map the categorical variable to the x-axis and the weight variable, or numeric one, to the y-axis, and we're going to say use stat equals identity to say the value that we want to plot is the value that appears in the weight column. Okay, so here we are. This is the data that we're looking at here, PG underscore mean. This is the actual data frame. This is what it looks like in, so you know what, let me clear out my environment from last class. Okay, so PG underscore mean. This is, it's just a 3x2 data frame, and we can ask help on PG underscore mean, and it will say it's the mean of results from an experiment on plant growth. So this data set, PG underscore mean, comes from the library. This is the wrong graph here. It comes from the library R Cookbook, the R graphics cookbook. So when you load up, if you're going to use a data set that comes in a package, okay, which is a lot of the times, at least for classes, right? So if you have questions about the data set, you can always ask help on the data set that you're looking at. So you can, like we have the Iris data set, which is one of the built-in packages, built-in data sets, and you can always ask help on the thing, and there will always be a help page that kind of explains the format of the data, right? So that's going to be useful if you're doing that. Of course, if you're pulling in your own data from a CSV file, you're not going to have a help page for that. And hopefully the source of your CSV file will give you some information about it. But anyway, this is what our data frame looks like. 3 rows, 2 columns. We just say we're going to map the X column, or I'm sorry, map the group column to the X variable, map the weight column to the Y variable, and the heights of those bars are actually going to be the height that appears, the value that appears there, and so we use stat equals identity. If you have 2 categorical variables, so here we're looking at some cabbage data, okay? You guys laugh, but a lot of statistical research was done using agricultural data. This was kind of the first use of statistics, and statistics gained its reputation of being a reliable source of information in these agricultural applications, right? So people did a lot of studies on probability for gambling, but then as far as statistics and collecting data, agricultural experiments, because we always needed to grow more food, and now we live in a time of plenty. So anyway, we've got 2 categorical variables. We've got the cultivar, C39 and C52, and then we have the date, day 16, day 20, and day 21, and we're looking at, I don't know, the weight of the cabbage that's being grown. I'm not quite sure. And so here, when we create our plot, we're going to say we want to look at this cabbage data. And of course, here we're calling ggplot on the data frame, cabbage exp. But you can always do cabbage exp piped into the function ggplot as well, right? So you can have dplyr do all sorts of stuff, and if it's going to output a table, you can just directly pipe that output into ggplot and graph it, if that's what you want to do. Here we're going to map the date column to X. So we will have 3 positions along the X-axis, one for D16, D20, and D21. And then we will have the weight column determine the height of the bar. And because we want to actually use these values, we're going to have stat equals identity. We have fill equals cultivar. Fill is going to be the coloring of the bar. So we have fill equals cultivar. And so this is a mapping. We're going to have one color for C39, another color for C52. And another option that we specify in geombar is position equals dodge, and that tells ggplot to put the bars side by side rather than on top of each other. So we do this, and this is what we get, all right? We have our 2 categories for cultivar, C39 and C52. Those, they get their default colorings of kind of this reddish salmon orange color, and C52 is what, teal? Something like that, okay? Aquamarine, what's the difference between teal and aquamarine? Aquamarine is more blue? All right. And, wait, what's that? Oh, topaz? Something? I don't know, all right.
It's a color.
It's a color, right? Okay, good job. Here, this is just to illustrate what geombar does if we did not use stat equals identity, okay? So normally, or not normally, but many times you'll have a big data set and you want to create a bar chart. And if you create a bar chart, generally that means first make a frequency table and then plot that, right? So here we've got some diamonds data. This is a data set that comes with dplyr. Almost 54,000 rows. These are like, we looked at 54,000 diamonds, and we graded them, and we said this is a 1/4 carat, and it has the ideal cut, and the color is E. I think the best color is D, so E is a pretty good color, and then clarity is like slightly included or something, which is not the best, but all right. Well, anyway, I don't know if you guys are ever in the market for diamonds. But there's, you know, they rate the diamonds on these 4 different C's, and anyway, we can look at this column cut, and we can say how many ideal cut diamonds are there, how many premium cut diamonds are there, how many good cut diamonds are there, and we will, if we take ggplot and we just say make a plot using mapping cut to the x-axis, and we don't say stat equals identity, this is what it does. It goes through and it tallies up and it says you've got over 20,000 ideal cut diamonds, about 14,000 premium cut diamonds, and what's that, 12,000 very good cut diamonds, and so on and so forth. And if it's just a fair cut diamond, not so many. And so this is the default kind of behavior of the geom bar geometry, is that it will go through a categorical column and provide summaries. Okay, versus over here, the column that we want weight actually carries numeric values, and we want that to correspond to the height of the bar. For that, we use stat equals identity. Okay. In addition to the other things that we've done, we can, choose to map one of the variables to the aesthetic attribute fill. Okay, so for bar plots, when you're thinking of the color of the bar, that's known as the fill color. Okay, because you'll see that as far as settings go, you can actually specify the color to draw the bar and the fill of the bar. The fill is, this attribute is fill. The color is actually an outline, the outline to draw the bar. And we generally don't mess around with that, but if you wanted to, you could set the color of the line used to draw the bar. But anyway, let's take a look at this. We're going to look at this data set, US pop change, okay, for US population change. And it goes through and it shows us how the different states, how much the population changed between if we ask for help on US pop change, it's between the 2000 and 2010 census, okay? And so we looked at each state and we said, how much did the population change? And so pretty much every state grew except Michigan. Michigan actually had decline in the population, and I get it, but I went to school in Michigan for my undergrad. Nice people. So anyway, this is what we have, and we're going to just look at just the top 10. So what we do is we're going to rank the change. So if you rank US pop change and you do this, it's going to do the smallest values will be ranked number 1, and the largest values get ranked lower. So we're going to just do the top 40, or I mean top 10. So we say the ranking has to be over 40, and so this will just be the 10 largest ones. And so this, after we do this, we get the 10 largest, the states with the 10 greatest population changes. Okay, so here we have that. And then we will say, let's map the abbreviation. So we got Arizona, Colorado, up through Utah along the x-axis. the height of the bar is going to be determined by change using stat equals identity. And then the color that we are going to use to fill the bar will be determined by the region. So there are more regions, but as far as the ones that had the greatest amounts of change, there were only two: the west and the south Okay, and so these, I guess Colorado is considered a west region state, and so this is what appears here. Okay, and that's what we have. So we have two colors, and they get mapped there. If we wanted to, we could map the actual variable change to the fill color. All right. So change is a numeric variable, and because it's numeric, now we have a bunch of different values. So we don't have two colors anymore. We have a gradient of colors, and so the smallest value in change is something around 15, okay? So as far as the top 10 states, 15 is about the smallest value, and the largest value is 35. And so this appears here, and we go from 15 to 35, right? And so 15 is represented by this very, very, very dark blue, almost a black color. And as the values increase, we can see them get lighter and lighter and lighter until we get to this sky blue, baby blue color for Nevada. If we wanted to kind of further emphasize the differences in the states, we can arrange the states rather than by alphabetical order or the order that they appear in our data frame. We can arrange them by one of the actual variables. Okay, so we can reorder the bars along the x-axis, and we can say, so let's just compare the differences between each of these commands. So we got ggplot here. It's x is abbreviation y, change is mapped to y, region is mapped to the fill. The difference between the previous one and this one is that we used the change column mapped to fill, and the difference between this one and the next one is that the abbreviation gets mapped to x, except we modify the abbreviation by using reorder. So we're going to use reorder abbreviation based on change. Okay, and so this will put the smallest first and the largest at the end. And that's still being mapped to the x variable. So we're still mapping the results of the abbreviation variable to x. Okay, change and fill is, y and fill are both mapped to change, and this is what we have. Okay, so we can see as the change increases and goes up, we can see the shade also go from dark to light, and the transition would be smoother, but there's quite a big jump between 25-ish to 35, and so the jump shading is also quite significant. If we wanted to, we can change the colors that get used. All right, so we can customize the colors for our scale here. Okay, so this is going back to kind of comparing to here. Here, the default colors are the this red and blue, and if we wanted to, we can specify and say I want this shade of blue and this shade of orange for the bar graphs that you want. Okay, and so here I'm using like hex colors, and if you're not sure, you can always just look up hex colors, right? And you go to Google and then you type it in and you say, I want this color. Okay. Oh, this is I'm clicking a static image or something. All right. So anyway, just go onto Google and type in hex colors, and if you want, you can look up UCLA's hex colors, and UCLA branding has we have our own template guidelines as far as colors that we should use for UCLA branded things. This is the official UCLA blue color and the official UCLA gold color, according to that. But anyway, this is what we have. Here I specified, oh, it got cut off, but basically for the scale, not fill manual, it's going to be a scale gradient manual. Okay, so here I've got scale fill gradient, and we were just kind of playing around with this in the other class. Okay, and then so, you know, we can go from red to blue, and it would, this didn't work. Scale fill gradient, why is this not working? Okay, there we go. So that goes from red to blue, and you can give it pretty much any set of colors that you want. You can say, I want to go from yellow to blue, and it will try to figure out the transition colors that apply here. You know, you want to go from white to black, totally allowed. Okay, although this is hard to see now, so not the best idea. Okay, I like. What does red to black transition? How does that look? I'm just curious. Okay, I don't know what I was expecting. All right, so we have that, and then here we can specify things like the color. This is going to be a setting, right? I'm not mapping it to an attribute. So here, if I say the color is black, you can see it will now draw outlines to the bars, which is, they're thin, but they're there. And actually, I would have to look up exactly what are the things that we can do. Let's see, line thickness, line, create your own discrete scale, scale color manual, scale fill manual, scale, all sorts of stuff. Okay, well, different different options there. All right, is this okay as far as bar graphs go? So again, we're just mapping different variables to different attributes, graphical attributes. We can also create line graphs, right? And so with the line graphs, here is, this is like some biochemical oxygen something. I forget what this data set was about. BOD, biochemical oxygen demand. I'm not quite sure what this is from, but it's biochemical oxygen demand data interpretation using sum squares surface. Okay, well, there you have it, from 1967. We have a few observations here. At time, I think these are days 1 through 7, and this was the demand levels. And we can create a plot. We're just gonna say we wanna map time to the x variable, or x-axis, demand to the y-axis, or y-attribute. And here we want to draw a line to connect our observations. And there's a result. Okay, so now this gives us a visual idea of how much, you know, it climbed, then it dropped, and it climbed back up, which may not have been obvious when we are looking just at the numbers themselves. Okay, so we have a kind of a more easier understanding here. As far as line graphs go, there are really just a few attributes you can mess around with. Okay, you can change kind of the color of the line, and maybe the thickness of the line, and maybe the dotting of the line, right? So whether it's a solid or a dotted line. So these are just some of the things that you can do here. We're going to look at, this is the tooth growth data set, which is, we looked at guinea pigs, and apparently we gave guinea pigs either orange juice or vitamin C, and we then measured how much their teeth grew, because orange juice and vitamin C somehow have an effect, maybe, on guinea pig tooth growth. So and then we averaged this up, we grouped by these things, and we summarized it, and we said, you know, what was the mean change in or length of their teeth? And so this is what we have. So we have kind of 3 points to graph for the orange juice and 3 for the vitamin C group, and we also have three different dosages. Okay, and so to plot this is what we do. We map the dosage to the x. Okay, so as dosage increases, we can see, so that goes from half to 1 to double the dose. The length of tooth growth goes along the y-axis, so that's what we have. And then whether they received, which supplement type, whether they received orange juice or vitamin C, will determine the color for the red or the blue lines. Okay, and that's what we have here with geom_line. If instead of changing the color, you wanted to change whether it was a solid or dotted line, let's say you don't have a color printer, but you're going to be doing things in a black and white thing, this is one way to do that. Okay, and if you want, you can do both, right? You can have another categorical variable being mapped to the color, and one being mapped to the line type. Can we change the line width? Let's see, line width. I don't know. Let's see, ggplot line width. Let's see. Changing width of the line. Okay, well, shapes and type lines. So we always go to Google and we just try to see, how do we change the line width? Those are thick lines. I don't know if we have the ability to change the line width for different segments, and I don't think we do. I think you can change the line width as a setting. That's just, but I don't think we can actually modify the line width for a line itself. What the trait is here, but that would be interesting if we could make the line width from here to here thicker and this one thinner. That is, you guys know the do you know about the Napoleon March to Moscow data visualization? All right, this is part of your history lesson in data visualization. This is considered one of the greatest data visualizations of all time. For real, I'm not kidding. Charles Joseph Minard? I don't know. Okay, French guy. He created this data visualization. This was back, when did he make this? In the 1800s at some point. 1869, this is when he drew this plot, and here it is translated into to English. And you look at this and you're not quite sure what it represents. It's actually a map, right? So over here we have kind of France, and this is kind of going through Poland and all sorts of stuff to get to Russia and Moscow, and so this path represents. So the line here represents the path that Napoleon's men or his army took to invade Russia. So you're not familiar with the European history, Napoleon tried to invade Russia and it didn't go well, and it was a major loss in it. But and the thickness of the line represents how many men or how many troops were in the army. And so you can see when they started, there were a lot, and as the march went on, the troops, some diverted, okay, and the troops got thinner and thinner and thinner as the marches went on. Whenever they kind of counted up, there were fewer and fewer who were able to go. And so by the time they reached Moscow, this was how many they had left, and then they had to retreat, and the black line represents kind of the path they took of retreat, and you can see how that line dwindles even further, okay? On top of that information being represented, this is the temperature that corresponds that was going on during the retreat. So during the retreat, you can see the temperature get colder and colder and colder kind of at each point in time, which took a harsh toll on the army here, okay? And so this was created in 1869 and is considered one of the greatest data visualizations as far as what kind of information can be communicated in a single graphic, right? And so I hope you guys compete in Data Fest. And as far as if you're going to compete in the data visualization category, you're going to have to think beyond bar graphs and line graphs, right? I mean, that might be part of your visualization, but generally they want to see innovative ways to present the data, right? What is an innovative way to present some kind of feature or aspect in the data, and this was a pretty innovative way. There's all sorts of other things, but that's what we want, right? Okay, so yeah, drawing multiple lines, we can do that. So we can alter the color, we can alter the line type, and I think we can alter the width, but I think the entire line will have the same width. You're not going to have this ability to change the width as the line is being plotted, unless you draw different segments and separate the segments out. Okay, let's talk about scatter plots. As far as scatter plots go, there's only a few attributes that you can change for a scatter plot. When we're talking about the dot, you can change the color of the dot, you can change the size of the dot, and maybe the shape of the dot, okay? And so I think for this, I just changed the color and I changed the shape, but yeah, the size of the dot can also be altered here. All right, so here we're looking at some just height data. We're graphing the year, the age of the person, okay? So we're looking at 12 through basically 18-year-olds, 12, 13, 14, 15, 16, 17, 18, and we are plotting their height. And so we can see as the adolescents get older, they generally get taller, okay? These are individuals, so I'm not individuals. Each dot represents an individual person, so it's not that we are tracing an individual going through the years, but it's just at this point in time we took the heights of 12-year-olds, the heights of 14-year-olds, the height of 16-year-olds, and we plotted this, and what we see in general is that the older kids are taller than the younger ones, okay, which matches our experience as well. Okay, if you don't like the default plotting character, if you don't like this shape, you can change that, and you can see the different shapes that are available. And so this is shape 21. If you're not quite sure what shapes are available, you can always go to ggplot shapes, and there's probably going to be an image that shows what shapes are available, okay? And R also has its R plot shapes. You can always kind of look there and see what different shapes you have. But really, we got circles and squares and triangles. That's about all we've got, okay? Oh, X's, there's not too much variety, right? You don't want your shapes to be too crazy, right? You don't want to use emojis. I don't know, maybe you can use an emoji scatter plot, and now that I think about it, that might be decent, because emojis actually convey information. Although I don't know who your judges are if they're not familiar with the emoji verse, right? Here we have the unicorn emoji to represent. Okay, all right. So you can change the shape. So here I've altered the shape size as a setting, but you could move the size into as an aesthetic attribute and map a variable to it. Okay, and if you would want to map a numeric or an ordinal variable to size, you don't want to use size to represent a categorical variable, would not go well. Okay, so here is it just the size. Here we have mapped the categorical variable sex to the color. Okay, if you had to, you could map a numeric variable to color, but I think color makes more sense for a categorical one. And so here we can see the red dots represent kind of females and the blue for male. And what we generally see is that, you know, for age 12, they're all mixed here, okay? But then as age increases by around 16 to 18, we definitely see kind of a partitioning between the heights of the men and the heights of the women. Okay, so I mean it's not super pronounced, but it's definitely exists. Okay. And if you don't have access to a color printer, then you would have to resort to using shapes. And so here we have triangles versus circles, although it's a lot harder on the eyes to kind of see this. Maybe you can map the colors and use like white versus gray or something like that. But that's what we have here, okay? So these were just a few examples. Again, my encouragement would be to check out the reference documentation. They've got all sorts of things. And then as far as other things you can do, you can look at the R Graphics Cookbook from Safari Books Online. And that's a great resource, okay? And you can combine information from different sources of data. And so I showed the other class this analysis that I did for, well, this was kind of an example thing, for logistic regression. So in another class I teach some logistic regression, and logistic regression you're trying to map, or you're trying to go from a numeric variable to a categorical one. So this is age being the numeric variable, and then CHD is presence of coronary heart disease, so whether someone has heart disease or not. And so that's coronary heart disease is a categorical one, right? And it's hard to really see. We generally see lower age, there's more down here, and then higher age, there's more up there. What we can do is we can say, all right, let's look at everybody between 20 and 30 and count, how many we have. And if we did that, there would be a total of 10 people. One of them has coronary heart disease. So if we do 1 out of 10, that's 10%. And then we can look at, from 30 to 35, and we can say like, what percentage have coronary heart disease? Like 13%. And if we, create that summary and create the plot, we would get some kind of relationship that looks like this. With logistic regression, we're going to try to fit a smooth logit curve. And so here I've plotted kind of the resulting line that results along kind of also fitting the same dots that we had earlier here, okay? So these same dots get fit here. And on top of this, we could plot the actual raw data that appears, and we can kind of see the general relationship. So there is an ability to kind of combine you know, plots and data things from even different data sources. But you know, to do that, you definitely want to check out the cookbook and kind of see if there are recipes that show you how to do something of this sort. All right, we'll end here for now, and good luck as you guys study for the midterm exam. We'll see you guys on Friday, and we'll see you then. All right.